So, good morning ma'am, good morning classmate. I am Seth G. Luingas and I'm here today to report to you about depression storage. So first, depression storage is the term applied to water that is lost because it became trapped in numerous small depressions that are characteristic of any natural surface. When water temporarily accumulates in low point with no possibility for escape as runoff, the accumulation is referred to as depression storage. The amount of water that is lost due to depression storage varies greatly with the land use. A paved surface will not retain as much water as recently furrowed field. As you can see here in this illustration, you can see the runoff of water is going directly to the lake. But due to the depression storage, some part of some of the water are trapped here and cannot find a way to exit and make another runoff. So the relative importance of depression storage is determining the runoff from a given storm depends on the amount of intensity of precipitation in the storm. Depression storage refers to small low points in adulting terrain that can store precipitation that otherwise would become runoff. The precipitation stored in this depression is then either removed through infiltration in the ground or by evaporation. Depression storage exists on pervious and impervious surface alike. However, depression storage is much greater on undisturbed pervious surface. Standard design and construction practices remove these natural depressions in order to promote drainage, which reduce depression storage. Depression storage assumes that all water has a chance to infiltrate or evaporate. If the soil surface has low infiltration capacity and hydraulic conductivity, and if the topography allows the surface storage, then water may be stored at the surface in small pools or depression. These water-filled depressions, called vernal pools, are often seasonal features that form because of Earth's water tables. These depression storage areas may become hydrologically connected during high water condition and develop a flow network to deliver water to streams or other surface water bodies. Depression storage refers to small low points in undulating terrain that can store precipitation that otherwise would become runoff. The precipitation stored in this depression is then either removed through infiltration into the ground or by evaporation. Depression storage exists in both pervious and impervious surface. The volume of water is in depression storage at any time during a precipitation event can be approximated as V is equals to SD times 1 minus E raised to T times PE, to where V is equal to volume of water in depression storage, is the maximum storage capacity of the depression, PE is the rainfall excess, and K is the constant equal to 1 over SD. The value of the constant can be determined by considering that if PE is equals to 0, essentially all the water will fill depression and dV over dP will be equal to 1. This requires that K is equals to 1 over SD. Estimate of SD may be secured by making sample field measurement of the understudy. Combining such data with estimates of PE permits a determination of V. The manager in which V varies with time must still be estimated if depression storage loss are to be abstracted from the gross rainfall and input. One assumption regarding dV over dt is that all depression must be full before overland flow supply begins. Actually, this would not agree with reality unless the location of depression were graded with the largest one occurring downstream. If the depression storage were abstracted in this manner, The total volume will be deducted from the initial storm period, just like what is shown in the figure below. Such postulates have been used in satisfactory result under special circumstances. If the overland flow supply rate or plus depression storage intensify equals to I minus F, where I is the rainfall intensity reaching in the ground and F is the infiltration rate, then the ratio of overland flow supply to overland flow plus depression storage supply can be proved equal to the O over I minus F is equals to 1 minus I raised to P E. This expression can be derived by adjusting O over I minus F is equals to I minus F minus B over I minus F. For further derivation, you can look for it in the written report that I have submitted. But in the outcome of the derivation, you can finalize a formula of O over I minus F is equals to I minus F times 1 minus I raised to negative I times PE o times PE. Then, depression storage deduction are usually made from the first part of the storm. The amount to be deducted is a function of topography, ground cover, and extent and type of blood development. During major storm, this loss is often considered to be negligible. Some guidelines for estimating depression storage losses have been developed based on the studies of experimental and other watersheds. Values for depression storage losses from intense storm reported by Hicks are 0.2 inches for sand, 0.15 inches for loam, 0.10 for clay, and for clay. Tolen and Kiefer have used values of 0.25 inches in previous urban areas and 0.0625 in for the pavements. Studies of force small impervious drainage areas by Wiseman yielded the information where mean depression storage loss is highly correlated with slope. This is easily understood since a given depression will hold its maximum volume of horizontally oriented. Using very limited data from small paved street and section, Turner revised the curves shown in the figure below. Other sources of data related to surface storage are available in the literature. So, factors affecting depression storage. Nature of terrain, where areas are no lateral surface flow, are obliquous characteristics of the land surface that control many ecosystems. High density of depression increases the surface storage capacity, whereas lower depression density increases runoff, thus influencing soil moisture states, hydrologic connectivity, and the climate-soil vegetation interaction. Slope. It's also in fact the potential depression storage of a land cover. Wiseman determined a relationship between slope on an impervious surface and depression storage. As the slope increases and approaches 4%, the depression storage may approach 0. Then the type of soil surface. The storm penetration depends also on the density of the type of soil due to it affect the amount of runoff and also limit the storm. The trap between depression storage varies differently between different type of soil. Antecedent rainfall. Antecedent rainfall also changes the soil formation, so the amount of current storm runoff will most be likely affected by antecedent rainfall. Time. The amount of time the rainfall happened also affect the depression storage due to the volume of storm runoff increase as the time of rainfall increase. Empirical estimates of depression storage for storms. For sand, as mentioned before, sand is 0.2 inches, loam 0.15 inches, clay is 0.10 inches, impervious area is 0.62 inches, previous urban is 0.25. For measuring the quantitative description of depression storage, Depression storage is a dominating storage element which accounts for most of retention on wasteland surface, watershed surface. Because of practical difficulties in making direct measurement and dimension of individual depression, the values of depression storage are either be assumed or indirectly estimated. The physical properties of a surface in terms of depression storage depend upon the surface configuration, which can be modeled with a set of elevation values given by a function of horizontal coordinates. Depression storage volume decreases with the slope of plot due to reduction in both number of depression and dimension of the individual depression. The three geometric properties depth, surface area, and volume also related to each other. The geometric properties of the depression exhibit a frequency distribution of what similar characteristicity. The observed frequency distribution can be satisfactorily described by the Weibull distribution. So why do we need study depression storage? So we can store significant amount of precipitation. We can know the effects of timing which runoff begins. We also have the idea of the impact, surface roughness, which control the speed with which runoff travel. The important parameters in runoff models such as WEPP and the SCS curve number approach. Abundant field data for crop field, very little data for natural land uses. Depression storage can be a significant storage element on watershed surface, accounting for retention of much water. Interaction of surface treatment, slope orientation, rainfall patterns, initial soil water conditions, and surface storage element, and resulting effects on runoff response, including the timing of outflow hydrographs, were considered in all spatial scales. In such situation, the parameters took on view which appeared to have physical meaning in terms of physical characteristics such as mean term of travel and mean depth of depression or storage. For example, for simple arid, more complex situation involving infiltration at a range of scales, from small plot to small watershed, modeling applications showed that response could still be estimated well with a simple holistic model. However, the parameters can take on the value which may not or have any physical meaning at all. In such modeling exercise, the mean time of travel was found be the most suitable and mean depth of storage was quite stable and recession constant was the least stable parameter. So here in the picture you can see the study of Richard Grimm and Cannon from Department of Earth Science measuring depression storage at Sunny College at Brockport. So here they are measuring the storage using roughness clinometer. So that's all. Thank you.